All right, so I'm going to come from a perspective of a early career researcher. And so one of the major ways we've been thinking about some of these topics in the lab has been hearkening back to a paper by Platt in Science in 1964. And so this paper introduces the concept of strong inference. And I'd like to use it as a framework for discussion today. And in it, Platt puts forward a fair number of strong opinions, and it's definitely worth a read, and it's a fast read and a fun read that begins with, scientists these days tend to keep up a polite fiction that all science is equal. It goes on to discuss grants and review, colleagues, things like this. But really, for me, the big thing that Platt did is introduce an example of a framework that you can think about science in that's hypothesis-driven, but also allows for an exploratory aspect. And so for this, Platt doesn't reinvent the wheel. He goes back, at the time, at least 400 years, to Sir Francis Bacon. He brings in concepts from Chamberlain and also from Karl Popper. And so we'll get into that in a few details. And so strong inference is useful because it follows a systematic and transparent recipe. And so it seems a little hard to reconcile that at first when we think about the fact that as scientists or researchers, our endeavor is to explore the unknown. So how do we dig into the unknown in any systematic way that doesn't get in the way of creativity or intuition or insight? And so here's one example. Say that you have a hypothesis. Now, to be very clear, and this came up in discussions yesterday in the evening, a hypothesis under Platt's definition is not a giant, broad-reaching research goal. It's a simple, falsifiable statement. And again, this borrows from Popper. A hypothesis is a falsifiable statement that has to be something that forbids certain outcomes in the world. The more a hypothesis forbids, the better the hypothesis. It is more daring, it takes more risk, it is more falsifiable. That being said, your hypothesis might not be right. And so you also need alternative hypotheses, even if you don't necessarily believe them to be likely. They need to be feasible and falsifiable. Chamberlain, the method of multiple hypotheses. And so you have your hypothesis and some alternative hypotheses, as narrow and focused as possible, and you devise a crucial experiment or collection of experiments whose sole purpose in life is to disprove each and every one of those hypotheses, including your own. So you might need multiple experiments to do this, but each one should be focused. You perform the experiment. This excludes one or more of the hypotheses. Go through this process until you're left with a hypothesis or a small bag of hypotheses that then, I should say that was the methods carrying out the experiment, that then from that collection of hypotheses, you have a branching tree of logic. Sir Francis Bacon, 1600, the organon. And so this idea, at the time he called the method of the signpost or the finger post, was the old term for it. And from this, we have the basis of a systematic method. Not all science will fit. There is no single solution. But I think we can think about reporting, transparency, frameworks from perspectives like this. And so let's go forward. One other point I wanted to briefly mention before going into the rest is Platt brings up many concepts, one of which is which measurements are effective. Already in the 1960s, there were errors of reasoning, as he put it, that focus on numbers. I am a computer scientist originally by training. I like numbers. And yet this mathematical box, as Platt describes it, as a way to constrain and define a problem is elegant and fine-grained, but flimsy. Numbers can lie, depending on how you frame it. And not even lie, but mislead, even unintentionally. Platt reminds us there is a logical box as well. It is coarse and it is qualitative, but it is strong. And so we need to think about our logic. This is another way of saying what I've shown on the previous slide. And specifically, when we perform any measurement, a measurement is useful, by Platt's argument, when and only when it is related to disproof. You can never prove a hypothesis. You can never confirm a hypothesis. Someone can always show up later and show that it's wrong, but you can certainly disprove one. And so this brings us to Rushton, who reminds us that a theory which cannot be mortally endangered cannot be alive. And now switching gears to the fact that I focus on machine learning and AI, I would update this for today to remind us that a model, a computational model, cannot be alive if we cannot endanger it. And so for this, we've borrowed heavily from Platt. And there's three major points that we've put out, I guess it was last year, when we introduced the notion of adversarial controls, where we must be our own adversaries to the models we develop. First, opening the black box. I will argue that for machine learning, or these computational models, there is no black box. A cell is a black box until you investigate it. The same with the model. There are techniques. And so this is akin to Platt's logical box. Does the model even fit our notion of logic? The method of multiple models is borrowed straight from Chamberlain's method of multiple hypotheses. Again, hypothesis is interchangeable with most models. Also from Sir Francis Bacon in the 1620. And then the straw model is a notion from Langley in 1988, introduces the idea of straw man algorithms, and I'll show an example of this, and also Popper's falsification. And so we argue these are three approaches, three controls that we need to be using, specifically in computational sciences such as machine learning. I believe it applies broadly to this audience, as we've heard so much about data science and analysis when we think about the data we collect. And I'll show two examples before wrapping up. And so the first example is from our own work, where we're looking at the black box. This was a study with a neuropathologist, and we were working on machine learning computer vision algorithms to detect the presence of different types of amyloid plaques in the brains of deceased Alzheimer's patients. There's at least two, in fact, three plaque types we're looking at. Two are shown here, a cord plaque in the middle of the image and a diffuse plaque in the corner. When you train a neural network to rapidly identify these plaques based on images like this, we can ask the network using a technique called saliency mapping to show us which pixels in the image told you there was a cord plaque. We never showed it these pixels, but this is what it shows us for its rationale. What about for a diffuse plaque? And from this, we can see that we're at least satisfying a logical criterion, that the model is making at least intuitive sense to us. There's more you can do to quantify this, and the field is just beginning to move in that direction. I also point out, in our case, we put this up on bioRxiv, and it was later, and also we put the data up fully on Zenodo. The study had already been replicated by others, not reproduced, but replicated on different data sets before the paper was accepted. And so a second example is the straw model. In April of 2018, a paper came out in Science on the prediction of reaction yields for chemical reactions. What you can see in panel A is 6 different machine learning methods showing various R-squareds at the prediction of the chemical reaction shown at the upper right. What we were able to show was we came to it with a simple straw man hypothesis, which was, what if you took those chemical reaction, the chemicals shown in the reaction, and replaced each and every one of the chemicals with a random barcode, removed all chemical features? Could the model still do as well? Was this a difficult data set or not? And it turned out when in multiple ways we replaced the chemicals with random barcodes that meant nothing, you were still able to get down to just about the second decimal point, identical R-squareds. And so as we talked about, this process is one that's difficult. It's difficult to work with colleagues on this and to try to convince people that something like this is a problem. Ultimately, we went through the formal process, the commentary, and this was picked up by blogs and other sources. I want to commend the authors for this paper in that they provided all of their data. And so likewise, in doing this, we provided all of the Jupyter notebooks behind the analysis that was part of this discussion back and forth. And so a reminder then that Platt gives us is, how do we choose our methods? Specifically, methods are part of a precise chain of induction of how nature works. Any method that is outside of that chain for the science we are doing is a perfectly good method, but is not applicable to the problem we are solving. And so the membership of a method in this chain of reasoning is the sole yardstick of its effectiveness in a study. By analogy, I think we should think about reporting standards this way. When we talk about minimal standards, and this is something that Harvey had mentioned, that transparent reporting should show this chain of precise induction of how nature works. And furthermore, there's plenty of ways now we can share the chain itself, at least in data science. I won't belabor this point. I'll leave this up later. I believe we're submitting slides for afterwards. There are many tools that we can use to encode the chain and to encode our logic and our reasoning. And so one final proposal, something I'd mentioned yesterday, is that anything we agree on today will be out of date tomorrow or next year. I know this for sure in machine learning, and I believe it applies to many of our endeavors. Core logic won't go out of date, but the ways in which we need to show it will. And so ultimately, we will do the best we can as researchers and scientists to be our own adversaries. But there are concepts from cybersecurity and other cases where others who are investigating what we do, either by reproducing it or by showing flaws in the reasoning, need to play a role. And so finally, this could either be at the institution level in terms of a red team, a group there to test what we do. This is all the more important for AI. This happens in an unofficial way across the community when we attempt to reproduce and use each other's work. But we can be organized about this. And so I've mentioned data scientists and data breakers. And finally, within our own labs or groups, notions from the technology sector where we perform regular code review is something that I think would be worth thinking about in the context of a requirement or a strongly recommended guideline for funded groups that work with data and code that can be pretty overwhelming if we don't regularly go in and check each other's work and show our logic. And so with that, I'll say thank you.